Anybody want to hand anything in? Just asking. Anything specific was due. I got a bunch of stuff on my.
Do you have a question?
Well, the specific question, we might answer it one-on-one momentarily after class. But is it just a general question?
It was on the.
Yeah, I think probably. And I'm good about office hours right before this class, so we have some kind of stuff to be good. Okay, so what I handed you out is actually what says on this slide. At the end of the semester, whether I've missed a few classes or not. Now, just so y'all know, what was it? So today is Monday. Friday I missed, and actually the previous, I don't know, anyway. Friday I had to go check on my mom. She was in the ER. So I met my morning class, and because they had a test on today. But then I was back, I live in Burlington, so I was back. So anyway, she had rotator cuff surgery a week ago tomorrow, and it's been, she lives on her own. It's been, I'm not the only child, but I feel like I'm the only child. Mm-hmm. Yes.
It's only one more with my grandma.
Yes, so it all works out, but we're kind of trying to figure this out together. So that's where I was, but we're fine. It's interesting that as I was getting ready for today's lecture, it's like, this has happened to me before, not like my mom, but just having to be gone or time crunch, okay? So today we're going to finish part 9, and you're gonna see that I'm gonna kind of go back and forth a little bit within part 9. And then we're gonna go to part 3, which is the size of atoms, and I think that we'll probably knock that out. And then when we meet Monday, we still have 2 more parts in Unit 4, and they're kind of short, so I hate to jinx ourselves, like we won't be here the full 50 minutes, but Monday's lecture shouldn't be that long. Part 10 is important though. Part 11 is kind of like, so then actually you guys are still on track to have your unit exam in here next Thursday, a week from Thanksgiving. And again, this is like deja vu when I've definitely been here before. That gives us, we have a 5th unit of material in here. Now Unit 5, there is no unit exam over it. But that will leave us Wednesday and Friday. Did I do that right? Wait, I think I might have gotten off somewhere. Monday the 2nd, Wednesday the 4th. So that should be 6. I have an extra day in there. So go ahead and pencil in 12/6, because we can lecture on that. I was like, I think we're better than this. Okay, yeah. So on Wednesday, we'll talk gases. Thursday, you'll take tests. Friday, we'll talk gases. And then actually that leaves us the following Monday, which is the, good Lord, I don't know. I wasn't thinking very good. That leaves us the following Monday and actually Wednesday. Do I have this off? I don't know. I might have to double check my dates. I do know that the 12th then, you guys are going to have your final lab in here, and it's one where you're going to get lab credit, but you're going to do some calculations before you leave, and keep your calculations. I'll look at them before you leave. And then kind of to reset ourselves, yes, you guys have your test on Friday the 13th, December the 13th. So.
Why? Oh, so it's not on Thursday?
No. Well, your final, comprehensive final exam, so that starts exam, that's finals, yeah. Yeah, the 12th, which is a Thursday, is your last day of normal classes, and you can see what we'll be doing, and then you'll come in and you'll take your comprehensive final the next day. You guys drew the short straw. They kind of have started going alternating evens and odds, as in kind of Friday and Monday final exams. So
we don't have class.
So not only like
5,
which is the Thursday.
12/5, you guys are having a test.
Oh, okay.
Yeah. But I think I missed a day in there because I have the 4th, which is Wednesday.
Next is the Friday.
Yeah. Yeah, I think you should put 12/6 right here. I really think you should put 12/6 right there. We don't have it all. And actually, I'm digging that because that probably means when we come in 12/12, I'm not going to have to do any more talking about gases. We've had 4 full days of it. Probably should be okay.
Why are we having finals this week? No, Friday.
I didn't make the schedule. There are a lot of things around here I don't have anything to do with, and that's one of them.
I don't have to have a final.
Yeah. So, but the way they are is they alternate, so we meet at an even hour of the day, Monday, Wednesday, Friday, and so you guys are on Friday. So if you have a class that meets like before this at 11, that's odd, not weird, but odd, and odd number, and you guys will have your test on for that class on Monday, so it kind of staggers.
So if I was right after this.
It'll be on Monday. Yeah. Okay, so I kind of picked out some slides to kind of get us kind of to finish up part 9. So yeah, you gotta go clear back, and you're gonna see I kind of skipped some slides. We already did this slide. But I wanted to revisit this idea of orbital hybridization, where remember these are atomic orbitals, so this middle column is showing you what an atom is taking of its own to hybridize, to spit out equal hybridized orbitals. And we said that actually it's the conservation of orbitals. So if it takes one of its s and 3 of its p's, it's going to have 4 equal hybridized orbitals. And then we talked about how that gives shape around it. That would be what? Tetrahedral shape. Okay. So this then slide is to try to kind of show you the blue is the carbon atom, and you can see the 4 things extending from the carbon atom. Those are 4 sp3 hybridized orbitals of that carbon atom. And we've talked about how covalent bonds are made by an overlap of atomic orbitals. So then the gold here is the hydrogen orbital, and the blue is the hybridized carbon orbital. So you can see right here, this overlap, that is the bond connecting this hydrogen with that carbon. Okay, so that's how that works. Electrons are shared in that bond orbital. So kind of switching it up, and I forgot to bring in my little structures, but C2H6 looks like this. So let's kind of see both of those carbon atoms they have 4 hybridized orbitals, must be sp3 orbital hybridized. So you can see kind of the overlap here between 2 of those carbon atoms are going to overlap their one each of their sp3 hybridized orbitals. So sp2 orbital hybridization takes 1 s and 2 p's, and actually in this case you can see instead of the sp3, sp2, I don't know if you can detect it, but it has a little more characteristic of an s, because now it's 1 s and 2 p's instead of 1 s and 3 p's. Okay, so we talked about how that type of shape, what do we call that shape?
Trigonal planar.
Yep, trigonal planar, very good. I've heard it pronounced a lot of different ways, very good. Trigonal planar, what's the bond angle? 120, yep, exactly. Yep. So this would be an atom that is getting ready to reach out and overlap these hybridized orbitals, or to form sigma bonds, or we can have lone pair electrons reside in these. Remember, lone pair electrons can also reside in hybridized orbitals. An example of that is BH3. And this is kind of showing you how that would work, the sp2 orbital hybridization process. Okay. In each one of these cases, if we were to pick the central atom, so in the first case it would be the nitrogen, the second case it would be that middle carbon, and the last place I could pick, I'll put a little asterisk here, it could be either carbon there. But one of the things that we've done is you can tell the structural geometry around an atom if you count sigma bonds and lone pair electrons. So in each one of these cases, I've got 3. I've got 2 sigma bonds, 1 lone pair electron. That's 3. I've got 3 sigma bonds around the carbon atom. I've got 3 sigma bonds around that carbon atom. So it's all sp2 orbital hybridization. You would tell me trigonal planar, bond angle 120. So now here we go. This is the other one I want you to know, sp orbital hybridization. And it gives this linear arrangement, bond angle 180. And this is how that would kind of look. The energy associated with these hybridized orbitals is greater than the s, but less than the p. And then we use this a lot in Thursday's Latin. where we talked about you count sigma bonds and lone pair electrons, and then you know the structural geometry, electron pair geometry. And I want to say just briefly about these other two guys. So we have SP, SP2, SP3. In expanded valences, we can have SP3D and SP3D2, and we get these funky shapes. Okay, so this is an example of an SP3D. And actually, can you see where this is SP3D2? SP3D must have, what, 5 things spreading from, in this case, the sulfur atom? I've got 1, 2, 3, 4 sigma bonds and 1 pair electron. That's 5 things. Here, this chlorine atom has 1, 2, 3 sigma bonds and 2 lone pair electrons. So I guess that's also a lot. Okay, so these are all, and here's another example of 5 things. Okay, so SP3D looks like that. Looks like that. Now we change it up a little bit. Instead of having kind of 3 around the equator, we have 4 around the equator. It's kind of how I think of it. That's SP3D2. We've got 6 equal hybridized orbitals reaching out. Okay. Now, one of the things I want to go back and revisit is this. So, if I were to put all of these up here, all of these structures, I'm going to put a little asterisk next to the carbon atom, a little asterisk next to the nitrogen atom, little asterisk next to the oxygen atom. And if I were for each one of those 3 to ask you how many sigma bonds and lone pair electrons, what would you tell me? 4. 4. In each case, there's 4. Yep. That's why at the bottom it says it has 4 sigma bonds, lone pair electrons in each case. So you guys would tell me what's the shape? Tetrahedral. What's the bond angle? 109.5. You would be solid on that, and I would say yes, ma'ams, because we have one in there. Okay, but I'm here to tell you it's not quite 109.5. Not for all of them. The only one that is exactly 109.5 is this one with methane that has equal things attached to the 4 things you told me it was. This right here, we're going to see that with one of those are lone pair electrons. Think of the lone pair electrons as being kind of being a little fluffier. And so it kind of makes the legs of the 3 hydrogens for ammonia kind of squish down a little bit. So here in a minute, I'm going to show you that this is a little bit less than 109.5. So here with this water molecule, again, you tell me 109.5 is the bond angle between that mix with that oxygen at the vertex and the 2 hydrogens. But again, those 2 lone pair electrons squish it down a little more, so it's even less than the bond angle for ammonia.
Well, like on a test, if we put 109.5, you won't count it wrong, right?
Yeah, that's right.
Okay.
I would totally not. 109.5 for sure, a little less than 109.5, and even less than 109.5. Yeah, exactly. I'm just here to kind of tell you there's a subtle difference. It's not much of a difference. Instead of 109, it's 107, then 105. Okay. All right. So I left this one in. I have no idea what was going on the other day. I still don't know. Hope I don't. Because, let's try it one more time. I'm a glutton for punishment. Pot of valence electrons. Chlorine. How many valence electrons for chlorine atom? Yep. Very good. Oxygen, there's 1. How many valence electrons? Yep. The charge? Yep. So I add 1. Yep. So I get 14. And how many electrons are shown here? I get 14 electrons. I have no idea what was the problem the other day, but I could not think of it. Anyway, we're okay. Okay. Yeah, and these are questions like we've been talking about. For either the chlorine or the oxygen, you always count sigma bonds, which is 1, pairs of lone pair electrons, which is 3. 1 plus 3 is 4. So you're back to this idea of sp3 orbital hybridization and tetrahedral. Then another slide I kind of kept was this one. I don't think we did this one. If you got your lecture notes, let's see what we can do with this one. So this is a question about bond angle. Now, to me, in order to do bond angle, I kind of start back at scratch. Like, how many sigma bonds and lone pair electrons are there? Then I know orbital hybridization, and then I know shape, and then I know bond angle. So we're going to kind of go from left to right. So this carbon atom, this one right here, how many sigma bonds? 4. How many lone pair electrons? 0. So what's the shape? Tetrahedral. What's the bond angle? Oh, it's tetrahedral sp3 and it's 109.5. Yeah. So you can see that second mark right there. Okay, I'm picking on this carbon atom. How many sigma bonds? 3. Yep. How many lone pair electrons? 0. 0 lone pair electrons are on that carbon. So 3 plus 0 is 3. So what sort of hybridization?
Trigonal planar. Oh, so
Trigonal planar, sp2, exactly. So what bond angle are we?
120.
120. Now there's a good example of when on paper and pencil you're like, it looks like a 90 to me. Like, no, it's 120. Perfect. So the last one, picking up the carbon atom, how many sigma bonds?
2.
2. Only 2 sigma bonds. We have sigma here, and if we have a triple bond, we have 1 sigma, 2 pi. How many lone pair electrons? 0. 0 lone pair electrons around that carbon atom. So 2 plus 0 is 2. So what sort of hybridization? Nope. What sort of hybridization? We only have 2. SP. SP, baby. Yep, just SP. And so if it's SP, what sort of shape do we have? Linear, and it's linear. What sort of bond angle do we have? 180, yep. Do a 180. Yep. You got it. So the test isn't made out yet for your unit exam, but sometimes I'll have like a structure like this drawn for you and ask you questions, kind of like you're doing on the sheet that's you're going to hand in. You can even hand it in when you come take your test. I'm fine with that for Lewis structure sheet for lab credit sheets. And what else I can say? Oh yeah, and the other thing on your test is you'll have I say simple Lewis structures to draw, okay? And the other thing you're having your test is the nomenclature. Well, I give you the name of a compound, you give me the formula, and I'll give you the formula, you give me the name. So you kind of know already what's going to be, but no calculators needed. Okay, and I don't think we need to spend much time on this. Well, I think you guys, are we okay with the carbon atom? How many sigma bonds? 3. Lone pair electrons? 0. What orbital hybridization? Trigonal planar, sp2. Yep, you guys got it. I don't know if you guys have that to fill in or not. Bond angle 120. Now it's symmetrical. The ones I'm going to show you, both the carbons have the same thing going on. So remember that a double bond has 1 sigma bond and 1 pi bond. And the pi bond is secondary, and it's called secondary pi bond for a reason because it kind of takes the space. The sigma's already there, so it takes kind of what's left over. Okay. So how about this one? Pick on this carbon atom. How many sigma bonds? 2 sigma bonds. Yeah, we have a sigma there, and with a triple bond, 1 sigma, 2 pi. So how many lone pair electrons? 0. So what sort of orbital hybridization? SP, perfect. Shape? Linear. Bond angle? Yep, 180. So SP linear 180 is what you told me. Perfect. Okay, yep. Now we are going back to bond characteristics. And it's like I said, it's just like I've been here. What I had to do last semester. Okay, so bond properties. And remember when we were in lab and you guys made your double bonds, your triple bonds, and I asked you, you guys told me the triple bonds seemed the strongest and seemed the shortest. And actually that's kind of what I need to cover relative to single bonds. Okay? So as long as you're comparing apples to apples, you have the same two atoms that are stuck together, like carbons do it all the time. A carbon to carbon triple bond is stronger than a double bond is stronger than a single. Okay. So you probably already have a sense of that. If you have a triple bond, how many sigma bonds do you have?
Sorry, one.
One sigma bond, yep, and 2 pi. And then in italics down there, it says that the primary, the sigma bond, is stronger than any pi bond. So if you can kind of tease like that with a triple bond, the strength. So here's just summarize what you guys just said, or what we said on the previous slide. The triple bond is greater than the double bond, which is greater than the single bond. With regard to bond energy, that's assuming you have the same two atoms that are stuck together. The next line, instead of picking on carbon-carbon, we're going to pick on carbon-nitrogen. A triple bond, double bond, single bond. It's got the same pattern. And most people kind of get that. This is just some energies associated with, these are an assortment of single bonds and some even double bonds in here. So I kind of think of this is your magic wand to break those two atoms. And it's in kilojoules per mole of bonds that have been broken. So that can come in handy. When bonds are broken, energy is required. When bonds are formed, energy is released. These are chemical bonds. It's the same thing with chemical bonds, or what we've been talking about, your intermolecular bonds that give you your phase changes. Okay. So how about length? And you guys told me, and I'm going to kind of reinforce, when you start adding pi bonds, actually the distance between the two atoms becomes shorter. So for the same two atoms, a triple bond is shorter than a double bond is shorter than a single. Okay. Down here, it says we're kind of changing it up. It says now we're changing atoms. Instead of having the same pair of atoms, if we change out the atom, and this probably makes sense to you, the larger the atom gets, the bigger the bond length, or the longer the bond length. Bond length will increase with the size of the atom increases. And actually, momentarily, we're going to go back and talk about how big is an atom. So, again, to summarize, for the same atoms that are stuck together, your single bond will be the longest, your triple bond will be the shortest. I'm showing it with carbon bonded to carbon and carbon bonded to nitrogen, same trend. Okay. And I think you guys had a question in Alta about at what point is the energy the minimum, and this is kind of talking about minimum energy. This basically says this has minimum or optimum distance between two atoms is where you're going to have the lowest energy. If you try to get them too close, you're going to have more energy, and if they get farther apart, they're going to have more energy. This is actually just kind of reinforcing what I've been talking about. The bond length here is given in angstroms. Down here it kind of tells you what an angstrom is. An angstrom is 10 to the negative 10th meters, or 100 picometers. So here we have side by side how long is the bond and how much energy is tied up in that bond. Carbon to carbon, carbon to nitrogen, carbon to oxygen. Kind of a weird carbon to oxygen. These actually will make a little more sense when we talk about the size of the atoms. In this case, we are changing out what is connected to a hydrogen, okay, and you can see the effect on the bond length. But remember, the bigger the atoms are as they're stuck together, the larger the distance between the two atoms. All right, follow the bouncing ball. Back to part 3. And I'm going to go grab something off my desk. And I'll probably do that. I don't think she really is.
I just guessed. Weren't there nice and hard?
How big is that atom? So if I were going to ask you, do you remember we talked about pieces that make up an atom, subatomic particles? Which piece of the atom, which particle gives it its volume? Would it be its electrons, protons, or neutrons? I'm thinking electrons is maybe what I heard. It is the electrons that give the volume. Because we kind of talked, relatively speaking, yeah, the nucleus is really small, so it's the electrons that kind of give the volume. So here's we talk about the volume of an atom. We're going to talk about radii from the nucleus out to the edge of where the electrons are, the electron cloud. So to get volume, we could take, and remember this part, as far as the test goes, you're not going to have to use your calculators, but we could get to the volume of an atom by taking the radius from the nucleus out to the edge electron cloud times pi times 4/3. That would give you the volume. Okay, so we've done a few kind of lines here. Now, this is another one of those where looking at the periodic table, I want to talk about a trend. But specifically, I want to just only focus on the group A elements. So I'm going to take these guys, I'm going to ignore my transition metals, ignore my intertransition metals, take those two columns, these 6 columns, and put them together. If I do that, like you can see, for the group A elements, the size gets bigger as you go from right back to left again, and the size of an atom will get bigger as you go down the group. Now, if you're like me, this is the arrow that I need to spend just a moment at the end of part 3 talking about. So in other words, let's make sure we're all on the same page. According to that top arrow up there, which would be bigger, sulfur or aluminum? How many people think that sulfur would be bigger? How many people think aluminum would be bigger? Yep, aluminum will be bigger. I'm going to kind of talk about why that is. Let's do another one. Which would be bigger, nitrogen or antimony? How many people think nitrogen would be bigger? How many people think SB, antimony, would be bigger? You're right. The one that gets us, and I'll try to explain why that is size increases this way across the period. I'll talk about why that is. Okay. All right, that's about it. The PM stands for what? What kind of meters? Picometers. I love that. Yep. So, sounds like Pikachu. Picometers. So yeah, you kind of see that actually right here we've got some diatomic elements. Fluorine's diatomic, bromine's diatomic, iodine's diatomic, and chlorine's diatomic. So it's kind of easy to get the radius, or excuse me, the distance between the two nuclei, and then to get to how big an electron cloud is for either one, the radius, all we do was take the internuclei distance and divide it by 2. So we would say that the radius of a chlorine atom is 99. Okay, so which one has the biggest radius? Iodine, exactly, and it makes sense. Okay, because up there you basically have these 3 and size increases going down. Yep. These are some nice little balls to kind of represent size. And again, we kind of see an odd trend in the group B elements, but we definitely see, well, this is an anomaly right here, but we see it gets larger as it goes across. Well, this looks like an anomaly too. That gets larger as you go across. That calcium looks smaller than that one, but larger it goes across in general. In general. This is a better look at the group A elements that I was telling you about. What group is missing? 8A is missing, yeah. So there are some exceptions. But in general, size gets bigger as you go from right back to left again in the same period. It clearly gets bigger as you go down the group. Okay. So we need to talk about both of those trends. The trend of increasing size going down the group, the vertical column, I explained by adding a crap load of electrons. Okay, so for instance, as we go from bromine to iodine, you're adding, what is 53 minus 35? A lot. Anyway, you're adding a lot of electrons, okay? Adding a whole bunch of more electrons, okay? So as you add those electrons, you're actually adding a whole set of electrons that have a higher end. We've talked about finding homes for electrons. The trend of size decreasing as you go from left to right, increasing as you go from right back to left again. That's something that here momentarily at the end of this part, I'm going to talk about something called effective nuclear charge. Okay, coming up. So we kind of talked a little bit about this when we talked about the what gives the size of an ion. We said that if this is an atom, and I'll go ahead and make a helium atom, I'll go ahead and put 2 protons in its nucleus, 2 neutrons in its nucleus. I'll go ahead and put a couple of electrons out like this. So it's the electrons that are going to give the volume to this helium atom. We have these attractive forces as electrons are drawn, negatively charged electrons are drawn to the positively charged nucleus where the protons are. Okay, if this force increases, then actually my size will decrease. And then we have the repulsive forces, where these electrons are repulsing each other. If that increases, then my atom will fluff out. Okay, so it's a balance of attractive forces making it small and repulsive forces making it large. Okay, so if attractive forces increase, it's going to make it smaller. Repulsive forces increase, it's going to make it larger. Okay. So as we hop, jump, and skip from left to right, okay, we are adding 1 more proton in the nucleus, and if it's a neutral atom, we're adding 1 more electron outside. So I need to explain using effective nuclear charge why, as we go from left to right, adding 1 more proton in the nucleus, 1 more electron in the electron cloud, why it actually gets smaller must have to do with these attractive forces increasing. Okay? So again, what makes it smaller? Attractive forces increase. What makes it larger? Repulsive forces increase. Okay. I think I've already said this. All right. So this is the sort of thing on your test too. Historically on my test, I will ask you something about the size, relative size of the atoms, and I'll ask you about the relative sizes of ions. And we already talked about ions. We said that if it's an anion, it's always going to be bigger than its parent because it's picking up electrons. If it's a cation, it's going to be smaller than its parent because it's losing electrons. But you could be faced with something like this on a test, and your best bet, and actually I'm going to show you a periodic table here in a minute, would be to use the periodic table you have on your test and circle those puppets wherever they are on the periodic table. And things will hopefully kind of start to fall into place. Okay, so we find these on the periodic table. And it looks like this. So what do you think? You got a 1 out of 5 chance of getting it right. What do you think is the smallest one?
Yeah.
Smallest one. I'm digging fluorine. Fluorine should be the smallest one. Yep. Which one would be the biggest one?
Oh, yes.
The biggest now. Yeah, I said fluorine smallest, biggest CS. Yeah, I agree. So we got that figured out. What about phosphorus and sulfur? Which is going to be smaller? Sulfur is going to be smaller. Yep.
Oh,
yep.
That's where the abnormality is.
No. Remember, sulfur and phosphorus, saying sulfur is smaller actually is applying the trend. Smaller to larger. Smaller to larger. Smaller, larger. So sulfur is smaller, phosphorus is larger. What about calcium? How would you compare it to phosphorus and sulfur? Larger. It actually is larger. because this kind of goes with a whole nother, we get a higher N for the electrons. Like sulfur has 16 electrons, calcium picked up kind of an extra shell. Calcium is going to be even greater than phosphorus. Okay, yep, smallest fluorine, the largest cesium, and between the sulfur, did I say that right? Fluorine, I'm sorry, fluorine smallest. Between sulfur and phosphorus, sulfur is going to be smaller than phosphorus. Then calcium is going to come, and then cesium. Sometimes people ask, yes?
Okay, what if you have like sulfur and then directly across from it there's like nitrogen, which is above it? So how would that work?
So which one's bigger between these
Yeah.
two? Okay. Yeah, she's right. Anytime you skip, if I'm just comparing these two, if I skip to a whole nother, this is where I'm adding a crap load of electrons, so it's going to be bigger. Yep. Yep. You got it. And there's the sizes of the atoms in picometers.
Why is it CE?
Syria? Oh, should be CS. Yeah, good catch. But it'd be the same trend, but yep, good catch. You should be one of those really, they look and they, I call those, look for mistakes in documents. Thank you. I would not be a good one of those.
Oh, I'm not good at spelling.
That's what spell check's for. It's the little things. Okay. So notice that as with the other trends, I kind of pull out the group B elements and I don't include them. So you can kind of see we have the 4th, 5th, and 6th periods. You sort of see kind of an odd sort of, not the trend I'm looking for. Okay. So the last thing I want to talk about, and I actually brought my notes because I like to kind of make sure I get this right on the board, is this thing called effective nuclear charge. The symbol for effective nuclear charge is Z star. So actually this is a thing. It's not a thing Mrs. Snipes made up, but really is Z star, effective nuclear charge. Okay? So what I think I want to talk you through is this phenomenon that happens. It's called shielding. So I have in my notes, I want to talk us through a magnesium and a phosphorus atom. So here's my magnesium atom. And magnesium is atomic number 12. So I'm going to go ahead and in my nucleus, I'm going to just put 12 P+, 12 protons. And then I'm going to start to say if it's neutral, it's going to have 12 electrons. And way back when, we said how those 12 electrons are configured. Where are the first 2 electrons? 1s2. Where are the next 2 electrons? Yep, 2s2. And then actually we have 6 electrons and then 2p, so 2p6. That brings us up to 10. And so where will my last electrons go? 3s2. Yep. And so here actually I'm going to go ahead and draw in my 2, search letter V, what do we call these guys? Valence electrons, very good, my 2 valence electrons. And actually these guys, these 10 electrons are inner electrons. Yep. So to calculate Z star, I'll put it over here because we can do this for anyone. What you do is Z star, you take the number of protons, which in this case is going to be 12, and from that you subtract the inner electrons. Sometimes these are called inner non-valence electrons, same thing. Okay, so effective nuclear charge here. I got 12 protons, and the reason I'm going to subtract, how many of these do I have? 10. Yep. So 12 minus 10. These are actually That gives me a plus charge of 2. Yeah, 2 plus. These guys right here, these inner electrons, these are what we call, these are going to shield. These will actually shield the valence electrons from the positive charge nucleus. Okay, I have a plus 2. All right, let's do the same thing for phosphorus. So how many protons in a phosphorus atom? I'm digging 15. Cool. And so how are the first 10 electrons configured? Yep, they're configured the same way, aren't they? After 2p6, let's see, that's 10 electrons, I need 5 more. 3s, not 5. 2, yep. Then where will the next electrons go? Maybe you need your air diagram for these. 3p3, I'm digging it. Perfect. Where are my valence electrons? They're here and, yep. These are the highest N, and those are my valence electrons. So I'm going to go put E, E, and I'll put E, E, E. How many valence electrons do I have? Yep. So 5 valence electrons. So how many shielding electrons do I have? 10. Yep. 10 non-valence electrons. So let's go ahead, I'm kind of running out of room. I'm going to go ahead and do the effective nuclear charge for phosphorus right here. What's the first number? 15. Yep, 15 protons. Minus, how many shielding electrons? 10. Yep. So I have an effective positive charge of 5 plus. So I'm going to put 5 plus here. I'm going to put 2 plus here. So the way this goes is each one of those valence electrons is being pulled in the top case to a plus 2, in the bottom case to a plus 5. Which one has the more attractive force? The plus 5. Yep. So if I was going to use an arrow to show that attractive force, this is greater. I might go like this, and this is less. I might go like this. Okay. So that's why even though it's got 15 protons, you're like, it must be bigger. Well, it's a busier atom, but actually its valence electrons are drawn more closely in, which makes its electron cloud smaller, which makes it small. And we just picked on, kind of randomly picked on magnesium and phosphorus. And it's following the trend that we said. We said that actually phosphorus should be smaller than magnesium. So that's how effective nuclear charge works. See what my other words up here say. Electrons in the same N don't shield from the nucleus. And I did check the Alta homework, and I think we're still on track for not having to move anything around, even losing a day. Any questions? That's all I have. Happy Thanksgiving break! Woohoo! Did you still have a question, or are you okay with your question?
I have a question. Do you have any extras of those?
I do.
I have one, and then I also have a question on this.
Okay. Hang on, let me stop recording this.